Hello everyone, welcome to the section for scientific computing. This is Professor Yi Zhu from Tsinghua University. The topic of this lecture is temporal difference learning for high-dimensional PIDEs with jumps. Let's welcome.
Thanks for Professor Ma for the nice introduction. And it's my great pleasure to be here. Okay, this is also my place. So today, I'm going to talk about how to solve high-dimensional problem with machine learning. So, so there are basically the audience, most of the audience I know pretty well. We are friends, students, and also colleagues. So as everyone knows, probably I put most of my time on wave problem, but today I'm going to talk about our recent results on machine learning. So this is basically the outline of standard machine learning stuff. Give something, a little bit about the introduction, and then about the methodology and the numerical experiments. Unfortunately, we don't have rigorous numerical analysis, and then I make some conclusions. At the very beginning, I just want to give the problem I want to study, the problem description. So I want to solve this argument, but this problem. This basically is a partial integral differential equations. So we have basically for this, the first three terms are the standard parabolic equation, and we have one extra term a. This is integral part, non-local part, due to the jump process. Okay, there is a, and we put all extra term on f. So f is a known function. So f could depend on the time, space, the state, u, and the gradient of the state. But there is, you see, there is also another part of the gradient state. The gradient of u, unknown function u, but how to split to their part or put it into their part is interesting. But anyway, the second derivative are here. So this is basically a Laplacian. Our goal, okay, I will talk about a little bit about the motivation of this problem. And the goal of this study, we want to propose a numerical method, especially a machine learning based numerical method to solve PIDEs with a very high dimension. For example, in our result, we solved for D equal 100 dimensions, so mean X. Okay, this is the goal. I just want to explain a little bit about the notation. As I said, B is the drift term corresponding to, if you know the SDE stuff. So B is the drift, this is diffusion, and this is non-local due to the jump, and F is the force. And we want to mention that we use the reverse version, means we don't put the initial condition, we put the end condition. So just due to the problem origin, the problem coming from the stochastic differential equations. So, and which one? This one? Oh, you miss that part is linear, totally linear. Okay. Oh, H is the hashing. So sorry. H. This is the hashing, basically. Okay. This is the hashing. Okay, sorry, I didn't mention that. Okay. So double derivative. And this is basically linear. Also, the non-local term also linear in U. The all nonlinearity I put into F. Could depend on, as mentioned, could depend on the state and the gradient of the state. Okay, this is the problem. So from the numerical point of view, this is a parabolic equation without non-local integrals. I want to say you can use a traditional numerical method for example, finite difference, finite elements, and for very high dimension, it's impossible to solve such high dimensional or parabolic equation. Use the traditional method. There's no way. And that and machine learning comes in. So PINN, physically informed neural network, and they potentially has the potential to solve such high dimensional PIDEs, but also has some. I just review a little bit. So also has some problem, and also related to deep galactic. They use residual loss to solve the argument to learn how to use the neural network to present to you, and they use residual loss to get the solution. And what I just want to mention that there is a very important paper about deep BSDE by Professor Han and Weilan E. This is also the FSA paper of this year in scientific computing, right? This year. So I think Professor Han also reported this result last week, and also what we call forward-backward stochastic neural network. They are very close, and also they use SDEs. When I say SDE, they basically use particle method. And just 2 years ago, Professor Zhen, okay, they also proposed, I can't remember his name, who also proposed TD-based neural network to use a reinforcement learning model to solve parabolic, without the non-local integral part. Okay, our work, we want to solve PIDEs with TD-based. Basically, our method is inspired by this paper. So they just solve parabolic equation. We want to solve the PIDEs. So that's the main difference. Okay, and then some motivations. Why do we need to solve such complicated PIDEs? So let's give a very simple example. So we know that Brown motion. I know some of you are experts in the stochastic analysis. I'm not an expert, but I try to give some explanation of this problem. So we know Brownian motions, they are independent stationary increments that follow the Gaussian distribution. So the path is continuous. So we're almost sure. And we also have some scale invariance. I mean, no matter how do you zoom in, you get almost the same structure. For example, if you use Brownian motion, you get standard Black-Scholes model for the option price, right? And why we want to use a model with jumps? So, for example, I give one motivation. We stock price over 3 years. You see there are two paths. One is from the Brownian motion modeled by Brownian motion. One is from the real data. So you see, you cannot tell which one. It's not very clear, but you cannot tell which one is from the real data, which one is from the model, from Brownian motion model. But if you zoom in, this is the stock price over 3 years, very long scale. But if you zoom in, stock price over 3 months, you can tell the difference. Okay, right? The left-hand side, this one is from the model. Means if you use Brownian motion to model the price, you get this kind of almost continuous path, right? But the real shows that there are many jumps. Okay. If you go to even stock price over 1 month, the left-hand side also the Brownian motion from the model equation, and this is the real. There is a big jump from there to there, right? Big jumps, and even every day, 1 day. So Brownian motion is continuous, but here many jumps. So that's why we need to consider the real problem. Means if you just use Brownian motion to model the evolution of the stock price, may not be a good model, right? So you want to add some jumps to the process. That's the basic motivation. So a little bit about Levy. Okay, so Levy process. Okay, the Levy process, we want to include jumps, so we use the Levy process instead of the traditional Brownian motion. Even though Brownian motion is very popular, basically many models use Brownian motion to model the stock price or other stochastic process because it's well studied, everyone can understand. But I say a little bit about Levy. Levy process, independent stationary increment, almost sure initial point is 0. And what's the main difference is that the stochastically continuous path is not continuous, it's just paths are continuous from the right and have left and limits. So there is jump from the left. That's basically the Levy. So, and there is a theorem we call the Levy-Eaton decomposition. That means if LT is a Levy process, they can be decomposed to the BT. This is a time dependent. You can see it's deterministic, and also there is a Brownian motion. Is a Brownian motion part, covariance matrix Q, and jumps, the jump part. So due to there is some stochastic analysis part, so their n tilde and n, they are different due to, we call there is for n is the Poisson random measure. So we have an expert here, so he probably know much better than me. Okay, and for n is the Poisson random measure, and but due to the standard definition can only define for A does not contain 0. If you contain 0, we have to introduce what we call the compensated Poisson random measure to include zeros. So that means we allow small jumps instead of just large jumps. We can allow very, very small jumps. But for very small jumps, the standard Poisson random measure for this definition cannot define for very, very small jumps. So we also have some jump measure from the Poisson random measure. Okay, this is not very important, just the standard stochastic analysis. I just copied from the book also, from Professor Duan's book. There is an expert on this part, so I could just copy some analysis part. Okay, then, our goal is to solve the high-dimensional PIDEs. So we want to collect or associate the PIDE with the SDEs. We use a particle method. So we don't want to, you really don't want to mesh. For put a mesh, you use the traditional method. We use the particle method. So we propose a Levy process, a Levy type process. So this is a sorry. So this is SDE with jump. You see, from the stochastic analysis, this SDE as a generator. The generator is the L. L, basically, you compare this L to the original PID. I should put here. Basically, it's this part. So we know this equation may come from some kind of a SDE. So we use that kind of SDE, except this F term. So due to the non-local term, if there is no A part, you use Brownian motion. SDE with Brownian motion, you can the PDF satisfies the first 3 terms. Okay, but with jumps, you need to add a Levy process. Okay, that's basically the idea. Okay, generator. So we can somehow to obtain the first term. The first term is the time evolution. So the second term, the third term, and the jump term. Okay, we have this generator, and we introduce 3 processes. Y is the U. take the value at t at xt. Xt is the process does not depend on your solution. So you just generate the process, right? You generate a process. This process. Y is the PDF, take the value as the path, right? So the Y, because U is unknown, that means the Y you don't know. Even though YXT is known, if you generate a path, you know XT everywhere, right? At any time, but YT you don't know. ZT is the gradient, or you introduce some three notation, and UT is I want to use UT to represent the nonlinear term. Why? Why I need to do this or explain later? Okay. Then I use the standard Eaton formula on YT. You just use the Eaton formula. You can get a DYT, right? DYT. So you do the Eaton formula, then DYT, it has this bracket. This bracket is the first 4 terms of our PIDEs. The only term, the bio also have some extra terms I need to deal with. That means you use the equation. You use bracket, you replace the bracket by this F, right? You represent this F. We know that this part records the original PIDEs, right? So the first 1, 2, 3, 4 part is and only the F. But this is satisfied by any path. XT. You generate a through process by any path, and some extra term I need to deal with. So basically, DYT satisfies this, even though you don't know what YT is, what the exact value of YT, but you know satisfy this kind of equation. And the YT must satisfy the terminal condition. Means the YT at the end satisfy GXT, right? This is the terminal condition. Okay. Why is this? You just use standard Eaton formula. You can generate such kind of dynamics for YT. Okay, and then you need to discretize. This is a continuous stochastic process, but I want to discretize from 0 to t, capital T. I discretize into T0 to T capital N. And then you can, the process XT you generate also can be discretized by the discretized form. Y discretized. Here, a little bit about the jumps, due to the jumps. A little bit about the jumps. The N, capital N is the number of jumps into the, in the time interval from 0 to Tn. Zj is the size of the size, Zi is the size of the ith jumps. So that means now we can do that. Give x naught from the very beginning. You can generate many paths, right? Use the SDE with jumps. A Levy process, you can generate many paths. But what about YT, ZT, UT? Because we don't know U. We don't know, YT is the U, take the value at the path, right? And we don't know ZT, we also don't know U, capital UT. UT is the non-local term. So we want to use the neural network. So this is a basic methodology. We use two neural networks. That means N1 and N2. N1 approximate U. N2 approximate the non-local term. Why this term? Because here you get, I use the continuous form because we have some term like that. Even because it's non-local term, theoretically speaking, because G is known, if you know U, you use neural network to represent U. Theoretically speaking, you can compute because the tilde is also known, the jump process is also known. So theoretically speaking, you know this, right? You can compute. With a known U, you can compute this. But this is a non-local integral. 100 dimension on the integral, you don't want to compute this one, right? It's really complicated. So we use another neural. The other neural to represent this term. So this is basic idea. This is U. But we know that you should compute N2. That means if you want a neural, suppose you know U, N2 automatically is known, right? But that means the two neurons have a collection. Basically, from one you can get the other. So we need to make constraint for N2 or about later. So basically the architecture of our problem is this. You have your input. You give some linear layer. We have some kind of residual net, some blocks. We use 5 blocks, saves that. Just a standard neural network structure. And we have a linear out, and we have output. We have 2 neurons output, N1 and N2. As I just mentioned, N1 and N2, they are not independent. They dependent on each other, so we need to put a constraint on each other. So we use this kind of property or manager. There are many ways to put this constraint. We use this mathematical property. That means it's necessary to impose a constraint on N2. So we use this Martinger property. That means your U on this filtration from Tn to Tn plus 1. This is we represent this by our neural, right? The expectation is 0. Why this is true? I don't know. I just copied the property, the standard property. So we use this, and we can use discretize to the. We can take the value. I just want to mention a little bit, make some comments. We need to take the expectation to the. We generate many paths. We use the summation to approximate the expectation. So to the final loss function. So we'll talk about this one. So that means now we put a constraint on neural. This is N1 is the U. N1 there is N2. So that means N2 and N1 are connected with each other by this kind of term. We want to make this term vanish, right, along any path. This is a constraint on your N1 and N2. Okay. Reinforcement learning. Okay. Talk a little bit about your reinforcement learning. As we know that RL, reinforcement learning, you must have a state space, you have an action space, and each one you want to you choose a good action to make your cost, right? Value function, and so on. I should mention that we don't need any action, so that we only have a state space. State space is the temporal and spatial or space. That means from 0 to capital T, and this is our full physical space and spatial temporal pairs. Usually, for example, for reinforcement learning, we need to choose what we call the transition probability from one state space to the other state space. The probability from one state space to other state space. But we don't need to compute this one exactly. Since we know that from T1x1, if at T1 the position is at x1, we know the probability to T2. Next time at x2, because SDE can tell you what the transition probability is, right? Exactly determined by the SDEs, but we don't need to compute this transition probability, even though if you use co-learning, what kind of reinforcement learning, some stuff like a Q value, whatever, they need to transition probability about this. But for our purpose, we don't actually need this one. So we can define our reward. We need to define a reward to do the reinforcement learning. Is a self-supervised learning. So the reward can be defined like this, just this one. Just like this one. It's like a residual part. It's like a residual. So we define this like our reward. So each time you put a reward. So the xt, make a summary. So xt is the state process from one state to the other state. Is at time t, take the value at x. The u is the value function, and the yt is cumulative reward process. That means the yt is basically you take the value at xt. Okay. And since we use the temporal difference learning, it's a time sequence. So the definition of reward is borrowed from TD learning. So each time we update our u is we will approximate u by neural network. How do you know which neural network, the parameterized neural network, how do you know which one is correct? So we want to make the residual loss. Or the TD learning, we make a TD error, very small, c. From you update your TD by this, you have a residual from state Sn to state Sn plus 1. Sn means Xn at Tn, you take the value at Xn. So the one step TD error, and you think if just from this one, you think once your u is exactly the solution of your differential equation, that means your reward is 0. U equals u as n. So this is basically, I can see the reward. I just want to mention that the reward is exactly the rest. This part is basically ytn plus 1 minus ytn. That means this one and this two they vanish each other. Okay. So we use the Eaton formula. So I just copy this one, exactly the same one. So I copy the original formula to this one. Okay. So now we have everything. We construct the loss function from Tn to Tn plus 1. Tn plus 1. So we have one we call the TD error. This is the loss. We call loss 1. That means we want to minimize the least square temporal difference error. This is our residual. You see, just this one, just this one. We want to minimize this part. And u Sn plus 1, we take the path, right? We already generated many paths. So we take the value of many paths and sum over all the paths, and the residual is also defined on path. Okay. And we also have some terminal condition. This terminal condition, because we know that this you can see this is analogous to the PIN, the physically informed neural network is like a residual loss, is a PDE loss. But we also have some initial loss or boundary loss, right? So this is like a boundary, this is like a terminal loss, it's like an initial loss. So we also put, that means your neural network at time t, at any path you generate should be the G terminal condition, satisfy the terminal condition. But and we also introduce we want to put some regularity, something like that. We not just satisfy the value equal to G, but we want to the gradient equal to the gradient of G if G has some smoothness, something like that. But anyway, in most cases, this loss 3 seems in our numeric experiments does not make much contribution to our numeric examples, but we don't know. You know that this stuff is completely scientific computing part. We don't have any rigorous analysis. So, okay, now we have, as I just mentioned, until we have two neurons, we have this constraint to calculate the neuron 1 and neuron 2. We have loss functions. Now we have loss for each Tn. That means you update for each Tn, you have 4 losses. But I also want to mention that for we can also extend, if you know a little bit about the TD learning, we know that there are not just one one step TD, we have a multiple step TD. We call lambda TD, right? Lambda TD earlier we can means you update with multi steps. So that does not make any difference. Just use multi step. This is our pseudo-codes. I just want to mention that compare. I just want to point out compared to the FSA paper by Han and what's the difference? I want to mention a little bit difference. Okay, so at the very beginning, we want to sample m Brownian motions. You can generate. It's not just Brownian motion, also jumps. So we use the jump, the SDE, generate many passes with jumps, right? Many m, and from time for each path from n to 0 to n minus 1. That means from 0 to capital T. We can update the state, and we can compute loss and use the computer loss or the losses. Just want to mention that the terminal loss, you don't know what GTN you update from one small temp difference loss from the next step. You don't know what GTXDN is because you have not reached the terminal. You don't know what XDN. We use just the previous step, so it doesn't matter. Once we arrived at the end, we use the exact GTXDN. So this is the difference. And also, and you many iterations, you can get converge to what you want. This is basically the idea. Compared to deep BSD, what's the difference? Okay. Deep BSD basically is a kind of a Monte Carlo method. So basically, it's like a shooting. They also generate some kind of SDE process, but even though they don't handle this kind of jump processes for the Brownian motion, they generate many paths, and from the very beginning, they want to compute the end of the whole process to x capital T, to the end, to see whether your neural network is very close to the G. Take the value of GXTN. If not, it's like a shooting. Whether you shoot the G, if you don't shoot, you update your parameter. If you don't shoot the G, so they need to compute the full trajectory to update, to do the updating. So the TD learning, you can update your parameter. For each time step, you can update your parameter. That's the main difference. So we can also, the other terminology is different. So I just want to mention that we only have one. We use only one approximation. This also we know Monte Carlo. If you want to approximate expectation, you must have many trajectories, right? Otherwise, your approximation is not good, even for very high dimensions. So here, we only have one approximation for this expectation. The rest, there is no approximation for expectations. That means this is directly related to how many paths you want to generate. You know, the more, the better, right? Your approximation is much better. So the rest, we use TD error instead of the expectation error. For deep BSD, all the errors are expectation approximation for over paths. That's the other difference. Okay, since as I mentioned that this is a purely numerical, we do not have any analysis on the convergence or convergence rate, anything else. So we just want to show you, this is a summary of the methodology, and I just show you how good it is. Okay, okay, the simulation and Levy process, this is just we use, but this, even though we propose that the method can be used for any jump process, I mean any Levy, but we for high dimensional Levy is really complicated, right? We use to generate a Levy process in high dimension. Basically, it's not a easy problem, right? Not a very easy problem. We use a very simple one. We call the compounded Poisson process to generate a Levy. So basically, it's just some process to generate a Levy. So there are many other ways to do it, but we choose the simplest one we can handle. Okay, let's talk about experiment setup. We use a neural net. Its input is D plus 1 dimensional temporal, spatial temporal space, and we use 5 residual blocks and 2-dimensional output on 1 and 2 neurons with touch as our activation function with standard Adam optimizer learning rate divided by 5 every 5,000 updates, and our metric means how good, how do you measure how good your method is. We use L1 relative error for Y0. Why? This seems not a good option because we want to solve U. Basically, you need to find your approximation, neural network approximate U and the ground truth. But for so high dimensional problem, we don't have ground truth usually, right? We don't have ground truth. But even though for some problem you can have explicit formula, but we still use L1 error for the initial state. We only compare we have terminal condition. From the terminal condition, how good is your starting point? We use that as our metric to see how good it is. Okay. And we can also compare the path. If we use the same random seed, we can compare the path, but we'll explain later. Okay. So standard 1-dimensional pure jump only jumps. There is no drift, no diffusion, only jumps. And we have also, you just use the standard. Then you only jump process, and YT is you take the value of the process. You can generate the jump process, and we use the standard compounded Poisson process. We use Gaussian, okay, from 0 to 1. And this is the relative error. Okay, how good it is? It's 0.02% relative error. It should be good, right? And we can also compare if for each jump, this is a random process. So if we keep the same random seed, we can compare the whole trajectory, the error. So basically, the trajectory also they fit pretty good, right? This exact because this one we have the exact solution. This is for 1D pure jumps, and also we test different problems. For example, we test robustness trajectories. That means each time how many trajectories you want to put. So that's very important. Since we only approximate the expectation by the summation of trajectories, only for the Martinger properties, and the rest is the TD error. So we don't need many trajectories to approximate it very well. So for example, the trajectory is 100 to 1,000. Seems theoretically speaking, if you use more trajectories, you can get your approximation better, but seems not exactly the situation. So you see M is 100 to 1,000, that's like 8 times, but the error seems does not increase significantly. Also the same order, right? The relative error, and also iterations. That means we have iterations. We have we have many iterations. I mean, each time that we generate, for each iteration, we generate such kind of trajectories. And also we can, from 0 to capital T, we can divide the time interval by n, right? We can we can buy 20, 40, 80. Same, the error does not depend on this m and significantly. They are almost the same order. But for iteration, if you iterate more, that means even though it's converged, but you still iterate, but the error can decrease, right? Due to the iteration, because converge, you can get more accurate results. But you see, we only iterate like 250, we can get very good result. That's what I want to mention. That you want to get more accurate results, you want to put more iterations. And we also test different Levy measure. For example, this Gaussian, I just mentioned that. You can also put this one and this exponential, and also other Bernoulli, and also normal, the Gaussian, and the exponential, uniform, and Bernoulli. And for different lambda is, you can think the intensity of your jumps, something like that. Okay. So for different lambda, different intensity each time you jump how high. Okay. So for different lambda, we seems that there is no significantly different. So this means our result also can capture different types of jump process. Okay, this is, we also compare the trajectories. So this is the same. Okay, we also test a TD step. That means we use one step TD error. We can use two step, maybe multiple steps. Same from one step, two step to 6 steps. So the relative error seems no big difference. Okay, and also what I just mentioned that because the title of my talk is high dimensional. You only test one dimensional. You cannot. So we test a high dimensional problem. So we use a high dimensional problem, and eventually our test for different Ds. So why we choose this? Because for this problem we somehow, because we intention is f. This is the f term. So we can choose special f. We can get the exact solution. So that was the exact solution, right? Then we can do comparison. So for one-dimensional problem, the relative error is still like 0.5%. It's pretty good. But I want to mention that because of our metric only uses the starting point as our. That means how good your starting point. That means you only shoot one point instead of the whole L2. For example, L2 norm. We use like a point norm, just at the exact point as our norm. So it's not. So the relative error is less, so could be acceptable. So, and for 100 dimension problem, we choose several paths, several trajectories. We can get also good agreement for several paths. And this I want to emphasize a little bit for different dimension D. So for two dimension, for one dimension I already showed pretty good. But if I increase the dimension from 2 to 100, see the times I need the times. So almost same order, but like just double, right? From 2 to 100. Why? Because we use exactly the same. Oh, I didn't mention that. Did I? Okay. I think the parameter setup is almost the same as this one from one dimension. So like 1,000 at most, or 1,000. M is 4 equals 2. Oh, this is N for 1,000 iterations, and for M is 500. Oh no. Oh, for 500, but this table is not correct. So we use of 500 paths, even for 100 dimensions. So you know, for Monte Carlo method, if you want to approximate your expectation for 100 dimensional integrals, how many paths you need to get a good approximation for expectations? You may have many paths, right? But since we only approximate our expectations use the martingale property, I don't know, there could be some magic happens. We only use 500 paths, we can still have a good approximation. Only that part, but the rest we don't approximate any expectation. We don't need any expectation. We use the TD error instead. But that's the big difference between our method and the deep DSD. Deep DSD basically. And the other difference I just want to mention that is that we can update our parameter by each time step. Not for deep DSD. They must update the parameter at the end of the whole procedure. So deep DSD is much slower than ours. This is also the other reason. Okay, so the performance. So you see the relative error, even though you think the relative error, your metric is not good enough, but we choose this one. So our metric error, y0 relative error. So from dimension 2 to dimension 100, there is no significant difference, right? So almost the same order. And the GPU time, a little bit double the GPU time due to, since we don't increase the path, we don't increase the iterations, we keep the same number of trajectories, same iterations. Why we need more GPU time? Because high dimensional problem, your parameters, your neural network parameter is much better. You from originally for 2 dimensional, you only from 3 dimensional, right? 2 plus 1 to this residual block. But now you have 100 dimension plus 1, so you have more parameters. So that means you need to optimize your parameter in a much bigger space. So you need more time. That's the reason why we don't need more iterations. We don't need more paths. So that's it. Okay, since I still have some time, so I make a conclusion. So basically, we have today I just proposed a TD learning for high dimensional PID with jumps. So basically, we propose a Levy type of process to characterize the linear part of your PIDs. What's the linear part? And you put the rest part, use the Eaton formula to get rid of, to collect your stochastic Levy process and your PIDs. And the difficulty I want to put with the non-local terms. So for non-local terms, we don't really compute the integrals. It's high dimensional integral, we cannot compute it. So with martingale property, use another neural network to represent it. And we use the reinforcement learning instead of either residual loss or deep BSD, the Monte Carlo method. So, and future work, as I said, we don't actually have any convergence analysis or convergent rate analysis. So we just this is scientific computing. We just put a standard, and this is or I mentioned that we also applied this problem to multi-agent relative investment game theory. We can do stochastic control. We can also do game theory with jumps, also with jumps. The main result in our first paper. I want to thank our collaborators. Liu Inu was my student, and Hailong Guo, University of Melbourne, and Xu Yang is also my colleague and my classmate. So in UCSB. So this is the main result. I think that's it. Thank you.
Okay. Thanks, Professor Zhu, for the passionate talk. We still have time. If you have any questions, please go ahead.
Your state space, of your state space, right?
Yes.
The D. So D could be very large, indeed. Yes. But in your learning, I saw that your input is D plus 1 dimensional, but your output is only 2 dimensional.
Yes.
It's a significant mismatching, right? But is that learning can generate some good result? I mean, this is the dimension is so, the D could be very, very big, very large. But the output is only 2 dimensional. Is that okay?
So your question, yes, I think it's okay. So there is no problem.
No problem. This is the dimension mismatching.
You basically, your network is just a parameterized. That means you parameterize like x1 to xd, right? You can put alpha 1, x1, alpha 2, x2, and a very complicated structure. You parameterize this u, right?
Yeah.
With many parameters. How many parameters? I didn't show about just some parameters. You want to find the most. You want to find some kind of the best parameter to approximate your problem, right? So, so what's your? I don't think this is going to be a problem.
The input is D plus 1 dimensional. Output is 2 dimensional.
Yes. Yes.
That's still okay.
That's still okay. No problem. Okay. The standard neural network stuff, right? So, parameters are embedded in this kind of architecture. Many parameters. Like for example, if you can find such kind of solution, alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, this linear combination of your coordinates, right? Yeah. You just find the best alpha 1, alpha 2, and 2 alpha d, right? This is standard.
But okay. But anyway, that would be related to did you test that? I mean, how many samples you can use for this training?
500.
500, only 500.
500. That's the magic. I don't know. So
no matter how it's D changes, you always use this.
500. Yes.
500.
Yes, 500. This usually you want to approximate the expectation. You need for 100 dimensions. I don't know. The scale is you want to Carlo, right? You want to Carlo, so you must have at least 1,000 or even 10,000 trajectories, even more, to get a good approximation of your approximation.
Okay.
But seems we don't need. The reason I think we don't need any. We don't approximate any expectation except marginal property, and maybe the marginal property can be replaced by other one. Not exactly the expectation. So
okay. So my last question is definitely you convert this original problem into this all those using those property, right? It's a stochastic process.
Yes.
But anyway, let's talk about the original PDE. So you're dependent. Do you know this exact regularity of your solution U? You depend on that, or is the jump process gonna generate what kinds of singularity into the solution of the U?
Oh, from PDE point of view, or PID, yeah, it's a good question. So, if what I can say, if f is not dependent on linearity, right? If f is that only depends on t and x without, or you see this is basically a second derivative, but our f can only depend on the u and the grad u is the lower derivative. So as long as f is not so complicated, right? That's standard algebraic. So I think if g is smooth enough, also this is linear. So I think it's
no problem.
No problem. I believe so.
Okay.
Because this is a kind of Hit equation, right?
Yeah.
Type of Hit equation is regularize your solution, right?
Okay.
So should be. As long as f is not very complicated, but we don't do any PDE-based analysis.
Okay. Thank you. Very
This was the reason we can approximate the solution use neural network. If the solution is really complicated, some singularities, neural network, you must do some special treatments. You can approximate the solution well. Otherwise, no hope. Okay.
Okay. Thank you.
Sure.
So thanks for the talk. Since I'm not very familiar about the neural network, I just have a silly question. It seems like you can approximate the solution U, and you also can approximate the gradient U and the unlocal term of U by some new stochastic persons. So why don't you simulate the Laplacian U?
No. We only approximate U.
Yeah.
And gradient U, you can use autograd to compute. That means the standard, you can use autograd to compute. Once you know U is parameterized by neural network, for example, I assume U is approximated by alpha1 x1 plus alpha2 x2 linear combination, for example. So but you don't know what alpha1 to alpha d are, right? You don't know. You will find the best alphas to get the good approximation. So you can do autograd. You can get, this is the standard autograd procedure. And we don't need to do this part as well. So, and why I just put there, so, okay, I just put there, so this CT is not, we can use, once you know YT, you can get CT.
Okay, thank you.
But for UT, it's not easy. Yeah. It's a non-local integral. You can do autograd. You cannot do auto-integral, right? That's the difference.
Okay.
So,
thank you.
Sure.
And another question is there any relationship between the Levy measure and the error? I mean, if the height of jump is not very big, is it possible to enhance your results?
we do a little bit of comparison for different, you just for the Levy measure. For example, for lambda, right? For lambda basically is the intensity of your jumps, something like that. So if you increase lambda, I don't know, for big jumps, so you cannot tell there is a significantly increase or decrease or something. So I pretty much treat them as the same order. Right? But this one, because this is so simple, so the jump is very small, so you can think it's almost very smooth. Also, because only you use one equation, so there also depend on many different equations, so I cannot tell. But I see for that particular equation we choose, we cannot tell the significant difference. So thank you. Sure.
Thanks, Professor. To start, I'm a senior high, so Chinese, please.
Okay.
您反复提到一个词儿叫 jump， 就是前面那个神经网络 natural network 那个流程图。
This one or
那个黄色。对，您说的 jump 是我可以理解为就是那个 linearly 啊，就是中间那两步那个画过来的箭头，因为那上面没有标注式。
不，jump 是这个样子，就是说，我也用中文回答，就是 jump 就是说你可能是还没学到，就是说，你像一些股票，它突然有些股票你知道，它突然之间一个唰一下拉升，突然一下啪就掉下来了，然后它有一个很突然的一个跳跃，这个叫 jump， 它是这个，比如股票价格，你看这个股票价格就是我说。
是因为那个股票的，就是按照数学的预测方法，它是这个 K 型图是比较就是正常的往前走，但是在实际问题中， 那个股票会突然出现断层，所以你用的那个账户。
对，这是 modeling 的，就是说数学。For real problems, there are many different aspects. If you want to do real problems, very good. So the first thing when you do apply math, the first thing you want to choose a proper model. 找一个合适的一个数学模型。
哦，拟合是吗？
不是拟合的问题，就是这个模型它描述了这个物理过程的一个过程。但是因为你可以用这种，所以用 Brownian motion to model， 那你得到的这个图啊，你不管你选什么样的 parameter， 就你可以拟合一些参数，得到的是这个图。但实际会发现，你会发现它不能得到这个现象。这个现象你不管用什么样的 Brownian motion， 你把参数取得最好了，你也得不到这个现象，因为你的模型，你这个模型的缺陷导致你没有考虑这些复杂的因素。
然后还有您提到那个为了解那个东西，然后提到很高维数运算，就是您设了一个 n， 就是好像是往回校准的次数，那个 n 它是固定的，还是说因为您往后那个 dimension 就维度算的越多，它的误差可能会越大？您是一个标准的往回算的，就每次都是这些，还是说它是可以随着那个上升发生一个变化的？
好，that's a good question. So, 这个 for one-dimensional problem, we use 50 iteration. 这是我想想，我这没写。这张 table 这应该是 n， 所以for TD step， 这是测试的。我们一般就是这个最外层的那个循环是用的是500次，好像是，就基本上是固定的。We test our robustness for this problem. We use 500， 外一层循环，就每一次你生成这个叫 particle method。You can think particle method， 你让一个粒子在那儿走啊走啊走啊走啊走，然后再让一个粒子走。我每次就让500个粒子，我 use 5 trajectory 500个粒子往那儿走，按照一定的你设定的规律，它该 jump 就 jump， 它一定概率反正 jump， 然后你再把这些粒子按照我刚才那些东西，你把它算一下，然后每次去 update， 是否这个粒子最后都走到了那个你所设定的那个目标，它没走，然后你去 update 一个参数，然后我们外面就只要 update 500次就能够得到一个 good approximation。
这样。
Any other question? Okay, next, thanks Professor Zhu again.